Beneath the surface, most of Earth remains unknown. We have mapped the craters of Mars in finer detail than we have mapped our own ocean floor. We have sent spacecraft beyond the edge of the solar system. And yet, just a few miles beneath the waves that lap against our shores, there are valleys and mountains and entire ecosystems that no human eye has ever witnessed. Tonight, as you settle into stillness, let us sink together, gently, slowly, into the deepest darkness on our planet, where the questions outnumber the answers, and where the unknown stretches wider than you ever imagined. Welcome to Let's Learn While You Sleep. Tonight, we descend beneath the waves into a world that is at once the most familiar and the most foreign place on Earth, our ocean. It covers more than 70% of our planet's surface, holds roughly 97% of all the water that exists here, and yet, by most scientific estimates, more than 80% of it remains unexplored and unmapped in any meaningful detail. That is a staggering thought. The very ground beneath the sea, the terrain that shapes currents and cradles entire civilizations of creatures we have never named, is less well known to us than the surface of the moon. And so tonight, we will travel together through what we do know, and more importantly, through what we do not. We will visit trenches so deep that if you placed Mount Everest at their bottom, its peak would still be submerged beneath more than a mile of water. We will meet creatures that manufacture their own light in a world where the sun has never reached. We will explore hydrothermal vents that rewrite the rules of life itself. And we will do all of this slowly, gently, as the world above grows quiet and your breathing settles into something soft and steady. Let us begin where the light ends. If you were to slip beneath the surface of the open ocean on a clear day, sunlight would follow you down for a while, illuminating the blue world around you in brilliant, shifting patterns. This uppermost layer, known as the epipelagic zone, extends from the surface to roughly 200 meters deep. And it is the ocean that most of us imagine when we close our eyes and think of the sea. It is where coral reefs flourish in shallow tropical waters, where schools of silvery fish catch the light and turn as one, where dolphins arc through the surface tension and sea turtles glide with ancient patience. Nearly all of the ocean's photosynthesis occurs here, driven by microscopic phytoplankton, organisms so small that millions can inhabit a single liter of seawater, and yet collectively they produce roughly half of all the oxygen in Earth's atmosphere. Every second breath you take tonight, in a sense, was made possible by these invisible drifters at the surface of the sea. But as you descend past that 200-meter mark, everything begins to change. The water darkens. The familiar blue fades into a twilight indigo. You have entered the mesopelagic zone, sometimes called the twilight zone, which extends from 200 meters down to approximately 1,000 meters. Here, the sunlight is too faint to support photosynthesis, and the creatures that live in this realm have adapted to a world defined by dimness. Many of them possess enormous eyes relative to their body size, evolved to capture every last photon of available light. Others have abandoned sight altogether and navigate instead through pressure changes, vibrations, and chemical signals dissolved in the water around them. Scientists estimate that the biomass in the mesopelagic zone, the sheer weight of living organisms, may exceed that of all the fish in the rest of the ocean combined. And yet, we have only begun to catalogue what lives here. It is, in many respects, the largest habitat on the planet, and one of the least understood. The twilight zone is not a place of emptiness. It is a place of patience, of creatures waiting in the dark for whatever drifts down from above. Below the twilight zone, the ocean crosses a threshold into true darkness. From 1,000 meters to approximately 4,000 meters lies the bathypelagic zone, the midnight zone, where no trace of sunlight has ever penetrated, where the temperature hovers just above freezing, and where the pressure would crush most human-made structures like paper. At 3,000 meters deep, the water exerts a force of roughly 300 atmospheres, which means that every square inch of surface at that depth bears the weight of nearly 4,400 pounds. And yet, life persists. In this eternal night, many organisms have developed one of the most extraordinary adaptations in all of biology: bioluminescence. Roughly 90% of the creatures that inhabit the deep ocean are believed to produce their own light through chemical reactions within their bodies. They glow in blues and greens, and, more rarely, in reds that most deep-sea eyes cannot even detect, giving those few species that can perceive red light a kind of invisible spotlight, a private illumination that others cannot see. Consider the anglerfish, that icon of the deep, which dangles a luminous lure from a modified dorsal spine, drawing curious prey toward its waiting jaws in the dark. Or the vampire squid, which, despite its fearsome name, is a gentle creature no larger than a football, cloaked in velvety black skin and dotted with photophores, tiny light-producing organs that it can flash in mesmerizing patterns to confuse predators. These creatures do not live in a barren wasteland. They live in a world of signals, of flickers and pulses, of light that carries meaning in a language we are only beginning to interpret. Marine biologists have observed that certain species of deep-sea jellyfish produce a cascade of bioluminescent flashes when disturbed. A burglar alarm, some researchers call it, designed not to frighten the attacker, but to attract something even larger that might, in turn, scare the attacker away. It is strategy, played out in light and darkness, in a realm where we have barely begun to look. And so the Midnight Zone hums with a quiet intelligence that we did not suspect for centuries and may not fully comprehend for centuries more. Deeper still, below 4,000 meters, the ocean floor begins to reveal itself. And what a floor it is. For most of human history, we imagine the seabed as a vast, featureless plain, a muddy expanse stretching from continent to continent with nothing of consequence to mark its surface. We could not have been more wrong. The ocean floor is among the most dramatic landscapes on Earth. It contains the longest mountain range on the planet, the Mid-Ocean Ridge System, which stretches for more than 65,000 kilometers through every major ocean basin, winding like a seam across the face of the world. It is longer than the Andes, longer than the Himalayas, longer than the Rockies, and for much of modern history, we did not even know it was there. It was not until the mid-20th century that oceanographers like Marie Tharp, working with Bruce Heason at Columbia University, began to piece together the true topography of the ocean floor. Tharp, studying sonar data with extraordinary patience and precision, created detailed maps that revealed not just mountains, but a rift valley running along the center of the Mid-Atlantic Ridge, a discovery that provided crucial evidence for the theory of plate tectonics and transformed our understanding of how the Earth itself moves and changes. And yet, for all that we have learned, the mapping remains incomplete. As of the early 2020s, roughly 23% of the global ocean floor has been mapped using modern multi-beam sonar, a vast improvement over the 5 or 6% that had been mapped just a decade earlier, thanks in large part to international initiatives like the Nippon Foundation GEBCO Seabed 2030 project, which aims to produce a complete map of the ocean floor by the year 2030. But that still means that more than 3/4 of the seabed remains known only in broad, satellite-derived estimates, with a resolution too coarse to reveal the canyons, seamounts, and volcanic formations that almost certainly lie waiting in the dark. Every time a research vessel drags a sonar array across an unmapped stretch of ocean, it discovers features that were never predicted. Underwater waterfalls of dense, cold water, cascading over abyssal cliffs, vast fields of manganese nodules resting on the sediment like scattered stones in a garden, and ancient underwater volcanoes called seamounts rising thousands of meters from the abyssal plain without ever breaking the surface. Now let us descend to the deepest places on Earth, the Hadal Zone, named for Hades, the ancient Greek god of the underworld. This realm begins at roughly 6,000 meters and extends down into the ocean's deepest trenches, carved where tectonic plates collide and one slides beneath the other in a process called subduction. The most famous of these is the Mariana Trench in the western Pacific Ocean, whose deepest known point, the Challenger Deep, reaches approximately 10,935 meters below sea level, or nearly 11 kilometers. To put that in perspective, if you could somehow transport the entire height of Mount Everest, all 8,849 meters of it, and set it at the bottom of the Challenger Deep, there would still be more than 2,000 meters of water above its summit. Only 3 crewed missions have ever reached the bottom of the Challenger Deep. The first, in January of 1960, carried Swiss engineer Jacques Piccard and United States Navy Lieutenant Don Walsh in the bathyscaphe Trieste. They descended for nearly 5 hours through absolute darkness, and upon reaching the bottom, observed through a small porthole what Piccard described as a flat fish lying on the sediment. A sighting that astonished the scientific community, because it suggested that vertebrate life could survive at pressures exceeding 1,000 atmospheres. More than 50 years later, in 2012, filmmaker and explorer James Cameron made the second crewed solo descent in the Deep-Sea Challenger. And in 2019, explorer Victor Vescovo reached the deepest point yet recorded at approximately 10,928 meters during his 5 Deeps expedition. In the sediment samples brought back from these journeys, scientists have found microbial communities thriving in conditions that would obliterate most known forms of life. Communities that feed on organic matter drifting down from the surface in what marine scientists poetically call marine snow, a slow, ceaseless rain of dead plankton, fecal pellets, and decaying fragments that can take weeks to reach the bottom. Even here, at the uttermost floor of the world, life finds a way. Amphipods, small, pale, shrimp-like creatures, have been found scavenging in the Challenger Deep, their bodies adapted to pressures that would compress most biological tissue into something unrecognizable. The hadal zone reminds us that life's reach is longer than our imagination, and that the boundaries we once drew for the habitable world were never boundaries at all. And yet, even as we catalogue the trenches and name the ridges, the ocean keeps its greatest secret in plain sight: water itself. The deep ocean is not simply a void filled with seawater. It is a layered, moving architecture of currents so vast and so slow that a single molecule of water sinking in the frigid North Atlantic may not return to the surface for roughly 1,000 years. This planetary circulation, sometimes called the thermohaline conveyor, is driven by differences in temperature and salinity, and it connects every ocean basin on Earth in one continuous winding river. Cold, dense water forms near the poles, where winter air chills the surface and sea ice expels salt into the water below, making it heavier, denser, until it sinks with a patience that defies imagination. It slides along the ocean floor, creeping southward through the Atlantic, curving around Antarctica, branching into the Indian and Pacific basins, warming gradually, rising almost imperceptibly over centuries. Scientists have traced portions of this circulation using chemical signatures, radioactive isotopes left over from mid-20th century nuclear tests, and temperature sensors moored thousands of meters below the waves. And yet, we still do not fully understand how stable this system truly is. Paleoclimate records suggest that the thermohaline circulation has slowed dramatically in the past, and some researchers believe it may have nearly shut down during periods of rapid freshwater input from melting ice sheets, events that coincided with abrupt climate shifts across the Northern Hemisphere. Today, as polar ice diminishes and fresh water pours into the Arctic and North Atlantic at accelerating rates, oceanographers are watching the conveyor with quiet concern, deploying arrays of sensors across the Atlantic at 26 degrees north latitude, a project known as the Rapid Array, operational since 2004. The data so far hints at variability, at fluctuations we are only beginning to interpret. The deep ocean, it seems, is not a static reservoir. It breathes on timescales we struggle to perceive, and its rhythms influence climate, weather, and the distribution of life in ways we are still learning to read. Consider for a moment the creatures that have made this darkness their home. Not the ones we have found, but the ones we have not. Current estimates suggest that between 1 and 2 million species inhabit the ocean, and yet taxonomists have formally described only roughly 240,000 marine species to date. The gap between what we know and what remains hidden is enormous, and it grows wider the deeper we look. In the abyssal and hadal zones, new species are discovered on nearly every expedition that deploys a remotely operated vehicle or a baited camera system. In 2019, a research team exploring the Atacama Trench in the southeastern Pacific filmed 3 new species of snailfish, translucent and ghostly, drifting at depths exceeding 7,000 meters. Their bodies so perfectly adapted to crushing pressure that they would not survive if brought to the surface. Their tissues are saturated with a molecule called trimethylamine N oxide, which stabilizes proteins against the distorting force of immense hydrostatic pressure. And these snailfish are merely the organisms large enough to notice on camera. The microbial world of the deep ocean is staggeringly rich and almost entirely uncharted. Sediment samples from the abyssal plains routinely yield bacterial and archaeal lineages that have no close relatives in any known database. Organisms whose metabolisms remain a mystery, whose roles in global nutrient cycles we can only guess at. Some of these microbes survive by consuming hydrogen generated through chemical reactions between seawater and rock, a process called serpentinization. Others feed on methane seeping through the seafloor or metabolize sulfur compounds vented from hydrothermal systems. Some appear to live so slowly that they divide only once every several thousand years, blurring the boundary between life and mere chemistry. Each sediment core pulled from the deep is, in a very real sense, a census of the unknown, and each census tells us the same story, that we have barely begun. The biodiversity of the deep ocean is not a chapter we are finishing. It is a chapter we are only now learning how to open. Somewhere beneath the sediment itself, another world awaits, one that challenges our very definition of where life can exist. Over the past 2 decades, deep-sea drilling expeditions have revealed that microbial communities persist not only on the ocean floor, but within it, buried in sediment layers hundreds of meters thick, in rock formations millions of years old. In 2010, researchers from the Integrated Ocean Drilling Program extracted living cells from sediment cores pulled from beneath the Pacific seafloor at depths of over 1.5 kilometers below the ocean bottom, in material estimated to be tens of millions of years old. These cells were alive, but only in the barest possible sense, metabolizing at rates so vanishingly low that some scientists describe them as existing in a state of suspended animation, persisting rather than truly living. The energy available to them is almost unimaginably small, and yet they endure. This deep biosphere, as it has come to be known, may contain a significant fraction of all microbial life on Earth, though estimates vary widely and remain a subject of active research. Some calculations suggest that the total biomass of subsurface microorganisms could rival that of all life on the planet's surface, though more conservative estimates place it somewhat lower. What is not in dispute is that this hidden ecosystem is enormous, ancient, and profoundly strange. It forces us to reconsider the boundaries of habitability itself. If life can persist in crushed rock beneath kilometers of sediment, beneath kilometers of ocean, in near total isolation from sunlight and surface chemistry, then the conditions we once thought necessary for biology, warmth, light, oxygen, organic rain from above, are not requirements at all, but merely preferences of the life we happen to know best. And this realization echoes far beyond our own planet. It whispers that oceans elsewhere in our solar system, beneath the ice shells of moons like Europa and Enceladus, might harbor their own deep biospheres, patient and silent, waiting in darkness that has never known a sunrise. And so we arrive at perhaps the most humbling truth the deep ocean has to offer, that after centuries of exploration, after sonar mapping and robotic descents and satellite altimetry, we have directly surveyed only a small fraction of the global seafloor in high resolution. As of the early 2020s, the Seabed 2030 project, an international collaboration aiming to map the entire ocean floor, reported that roughly 1/4 of the seabed had been mapped to modern standards using multi-beam sonar. The rest remains known only in broad outline, sketched by satellite-derived gravity measurements that can detect the gravitational signatures of large undersea mountains and trenches, but cannot reveal the fine details. The individual hydrothermal vents, the cold seeps, the small seamounts and fracture zones where unique ecosystems may flourish unseen. We know more about the surface topography of Mars and the Moon than we do about the floor of our own ocean. This is not a failure of curiosity, but a testament to the sheer difficulty of the task. The ocean is opaque to the electromagnetic radiation that makes mapping other worlds from orbit relatively straightforward. Light, radar, and most other remote sensing tools cannot penetrate more than a few hundred meters of seawater. Sound travels beautifully through water, which is why sonar remains our primary tool. But mapping with sonar requires ships moving slowly over the surface, sending acoustic pulses downward and listening for their return, a painstaking process that covers ground at the pace of a walking human. At that rate, mapping the remaining 75% of the seafloor would require decades of continuous ship time and international cooperation on a scale rarely achieved. And yet the effort continues, quietly, persistently, one sonar pass at a time. Because what lies beneath those unmapped waters is not merely geography. It is the last great unknown territory on Earth, a darkness that still holds more questions than answers. And that, in its patient silence, reminds us how much we have yet to discover about the world we call home. There is a question that has lingered in the minds of oceanographers for more than a century. One that grows only more fascinating the deeper we look. What lies within the ocean's great trenches? Those long, curved scars in the Earth's crust, where tectonic plates slowly dive beneath one another. The Mariana Trench, located in the western Pacific Ocean, reaches a maximum known depth of approximately 10,935 meters at its deepest surveyed point, a narrow slot in the seafloor known as the Challenger Deep. To place that depth in perspective, if you were to take Mount Everest and set it gently into the Challenger Deep, its summit would still rest nearly 2 kilometers beneath the ocean surface. And yet, even at those crushing pressures, roughly 1,000 times the atmospheric pressure we experience at sea level, life persists. In 2012, filmmaker James Cameron descended alone to the bottom of the Challenger Deep in the submersible Deep Sea Challenger, becoming only the third person in history to reach that point, after Jacques Piccard and Don Walsh accomplished the feat in 1960 aboard the bathyscaphe Trieste. What Cameron found was a landscape of pale, fine sediment, eerily still, with very few visible organisms during his brief time at the bottom. But subsequent expeditions using uncrewed landers and sediment traps have revealed thriving communities of amphipods, small, translucent crustaceans, and dense populations of foraminifera, single-celled organisms encased in delicate mineral shells. Scientists believe that microbial life in these hadal trenches may play a significant role in deep carbon cycling, slowly processing organic matter that drifts down from the sunlit world far above. Some researchers propose that the trenches may harbor unique chemistries and novel metabolic pathways we have not yet characterized, because so few samples have ever been retrieved from these depths. The trenches remain, in many ways, less visited than the surface of the moon, and what they still conceal is a question that settles over the mind like sediment over stone, slowly, quietly, without resolution. And then there are the sounds, the vast, mysterious acoustic tapestry of the deep ocean, a realm we once imagined to be silent. For most of human history, the phrase, "the silent deep," seemed self-evident, a poetic truth requiring no examination. But when the United States Navy began deploying networks of underwater hydrophones during the Cold War, originally designed to detect the movements of Soviet submarines, researchers discovered something unexpected. The ocean was anything but quiet. It was, in fact, a world saturated with sound. Whale songs traveled across entire ocean basins, low-frequency pulses of communication spanning distances of hundreds, even thousands of kilometers through a phenomenon known as the SOFA channel, a layer of water at roughly 700 to 1,000 meters depth, where sound speed reaches a minimum and acoustic energy becomes trapped, bending back and forth in a natural waveguide. Blue whales, the largest animals ever known to have existed, produce calls as low as roughly 14 hertz, below the threshold of human hearing, and these infrasonic pulses can propagate across extraordinary distances. And yet, scattered among the known biological sounds, oceanographers have recorded signals that remain unexplained to this day. In 1997, the National Oceanic and Atmospheric Administration detected an ultra-low frequency sound in the southern Pacific Ocean, later nicknamed the bloop. it was one of the loudest underwater sounds ever recorded. And while scientists later determined it was most consistent with the sounds of a large icequake, the fracturing and carving of Antarctic ice, its initial mystery captivated the public imagination. Other sounds, such as the one designated Julia, recorded in 1999, and the so-called upsweep, first detected in 1991 and still recurring, have similarly been attributed to ice or volcanic activity, though some remain only partially explained. The deep ocean hums with a voice we are only beginning to learn how to hear. A continuous murmur of geological restlessness and biological conversation that drifts through the darkness like a lullaby sung in a language we do not yet fully understand. Consider now the mapping of the ocean floor itself, an endeavor that reveals just how little we have truly seen. As of recent estimates, only about 23% of the global ocean floor has been mapped to modern high-resolution standards using multi-beam sonar, a figure that stands in sharp contrast to the surfaces of Mars and the Moon, which have been mapped in far greater detail using orbital instruments. The Seabed 2030 project, a collaborative initiative launched in 2017 by the Nippon Foundation and the General Bathymetric Chart of the Oceans, aims to produce a complete high-resolution map of the entire ocean floor by the year 2030. But the sheer scale of the task is staggering. The ocean covers approximately 361 million square kilometers, and mapping it requires ships to pass over every stretch of seafloor with sonar instruments that send pulses of sound downward and measure the returning echoes to build a picture of the terrain below. What has been mapped already has revealed wonders. Vast underwater mountain ranges like the Mid-Atlantic Ridge, stretching roughly 16,000 kilometers along the floor of the Atlantic Ocean, one of the longest geological features on Earth. Autonomous underwater vehicles have discovered seamounts rising thousands of meters from the abyssal plains, each one a potential island of biodiversity, hosting corals, sponges, and fish species found nowhere else. Some scientists believe there may be more than 100,000 seamounts taller than 1,000 meters scattered across the world's oceans, and only a small fraction have been surveyed in any biological detail. Each unmapped square kilometer of seafloor is a place where no human eye and no instrument has ever looked. It is a silence not of emptiness but of patience, as though the ocean floor is simply waiting, unhurried, indifferent to our curiosity, holding its secrets in the soft, ancient sediment that has been accumulating, grain by grain, for millions upon millions of years. Perhaps what draws us most deeply into the mystery of the ocean is not any single creature or trench or uncharted ridge, but rather the feeling that the sea operates on a timescale so far beyond our own that it renders our explorations beautifully, peacefully small. The abyssal plains, those vast, flat expanses that make up roughly 40% of the ocean floor, accumulate sediment at a rate of roughly 1 to 2 centimeters per 1,000 years. This means that the soft, clay-like blanket covering the deepest portions of the Pacific Ocean basin may represent tens of millions of years of quiet deposition, particle by particle. The skeletal remains of radiolarians and diatoms and foraminifera drifting down from the sunlit surface in what marine scientists call marine snow. This slow, continuous rain of organic matter is one of the primary mechanisms by which carbon is transported from the atmosphere and surface waters into the deep ocean, a process sometimes referred to as the biological carbon pump. Current evidence suggests that this pump plays a significant role in regulating Earth's climate over geological timescales, locking away carbon in deep sediments where it may remain for millions of years. And within those sediments, researchers have discovered microbial communities surviving in conditions of extreme energy limitation, metabolizing so slowly that their cell division may occur only once every hundreds or even thousands of years. These organisms, if we can even call them that in any familiar sense, exist at the very boundary of what we understand life to be, not dead, not dormant, but persisting in a state of such profound slowness that time itself seems to lose meaning. It is a kind of patience that the human mind struggles to comprehend, and yet it is happening right now, beneath kilometers of dark water, in silence and in stillness. as it has been happening since long before our species first looked out at the sea and wondered what lay beneath its restless, shimmering surface. There is a region of the ocean that scientists sometimes call the hadal zone, named for Hades, the ancient Greek god of the underworld, and it begins where the abyssal plains end, at roughly 6,000 meters below the surface, plunging downward into trenches so deep and so narrow that they exist almost as worlds unto themselves. The Mariana Trench, the deepest known point on Earth, reaches approximately 10,994 meters at its lowest surveyed point, a place called Challenger Deep, named after the HMS Challenger expedition of the 1870s, which first began to reveal the true depth of the ocean floor. And yet, even now, fewer people have visited Challenger Deep than have walked upon the surface of the moon. The pressure at those depths is staggering, roughly 1,000 times the atmospheric pressure felt at sea level, a force so immense that it crushes most conventional instruments and demands engineering of extraordinary precision. And still, life persists there. Amphipods, small crustaceans no larger than a human thumb, have been found scavenging along the floors of hadal trenches, their bodies adapted over millions of years to withstand pressures that would obliterate almost any surface-dwelling organism. Xenophyrophores, giant single-celled organisms that can grow several centimeters across, carpet portions of the trench floor in delicate, lattice-like structures, quietly recycling organic matter that drifts down from the sunlit world far above. Some researchers have even discovered microbial communities thriving within the sediment itself, feeding on chemical compounds rather than sunlight. Existing in a metabolic state so slow and so patient that it challenges our very definitions of what it means to be alive. Each trench is isolated from its neighbors by vast stretches of abyssal plain, and this geographic separation means that the organisms found in one trench may be entirely absent from another, even one relatively nearby. The hadal zone, then, is not a single environment, but a scattered archipelago of extreme habitats, each evolving in its own silence, each holding secrets that we have barely begun to ask the right questions about. And beyond the trenches, beyond the known catalogues of species and the sonar maps that sketch the bones of the seafloor, there lies a question that is perhaps the most humbling of all. How much of the ocean's biology remains entirely unknown to us? Current estimates suggest that somewhere between 1/3 and 2/3 of all marine species have yet to be formally described by science, and some marine biologists believe the true number of undiscovered species may reach into the millions. Each year, research expeditions return with organisms that fit no existing classification, creatures whose biochemistry hints at evolutionary pathways we have never encountered, whose anatomies suggest adaptations to conditions we are only beginning to understand. In 2005, researchers aboard the Census of Marine Life program, a decade-long international effort involving more than 2,700 scientists from over 80 nations, reported discovering thousands of previously unknown species, from translucent octopods drifting through the midnight zone, to bacteria living in superheated fluid near hydrothermal vents, at temperatures exceeding 120 degrees Celsius. And that census, ambitious as it was, sampled only a fraction of the ocean's volume. Consider the mesopelagic zone, the twilight layer between 200 and 1,000 meters deep, where sunlight fades to a faint, spectral glow. Scientists estimate that this single layer may contain roughly 10 billion tons of fish biomass, perhaps 10 times more than previous estimates suggested, much of it composed of small, lanternfish-like species that migrate vertically each night in the largest animal migration on Earth. These creatures rise toward the surface under cover of darkness to feed, then descend again before dawn, a rhythm repeated across every ocean basin, every single night, largely unseen by human eyes. The mesopelagic zone alone could reshape our understanding of ocean carbon cycles, nutrient distribution, and global climate regulation, and yet it remains one of the least studied habitats on the planet. The ocean, it seems, does not merely hold mysteries at its edges. It holds them everywhere, patiently, in every layer of its vast and quiet body. And so, as we rise slowly from the deepest trenches, ascending through the midnight darkness, through the faint twilight shimmer, through the last pale shafts of sunlight filtering down from a world that now feels very far away. Let the ocean's quiet vastness settle over you like a blanket. There is so much we have not yet found, so much that waits patiently in the dark, not demanding to be discovered, but simply existing, as it has for millions upon millions of years. Let that thought be a comfort tonight. The world is larger than we know. The mysteries are gentle ones, and there is no urgency to solve them all at once. Let the slow rain of marine snow drift through your thoughts, and let the deep carry you gently, softly, into sleep. If the ocean's quiet depths brought you a little peace tonight, we would love for you to stay with us. Leave a gentle note in the comments about what you would like to explore next. Thank you for spending your night with Let's Learn While You Sleep. Subscribe and come back tomorrow night. We'll be here. Sleep well.